Hey there, I'm back with Dr. Tony Swinehart for another fossil video. So, what are you going to tell us this time?
Well, we're going to talk a little bit about interpreting fossils that are embedded in rocks because a lot of people think they're seeing footprints of birds and hieroglyphics and all kinds of crazy things. And we sort of need to think about rocks in 3 dimension and what they look like when you cut them or round them off in a rock that's been tumbling in the waves and kind of try to figure out what they really are.
Oh, okay. That sounds good.
All
Let's do
right,
it.
let's try it. Okay, I thought we'd talk a little bit about interpreting fossils that are embedded in rock. And so many of you probably hunt rocks on the beach. And they're typically rounded. They're rounded in part potentially by glacial activity and certainly by the erosive force of waves. It's basically a giant rock tumbler. So you get these rounded off bits of rock. Well, that started out probably something that looked a little bit more like this. And this started out as a continuous layer of sea bottom, soft sea bottom, that has later, with the accumulation of more and more and more and more sea bottom, has been compressed, and in some cases petrified into rock, petrified so to speak. And then at some point, either there was tectonic upheaval, and this what was once flat seafloor ends up being raised up into some kind of exposure, and you either have erosion or freeze-thaw dynamics, breaking bits of this off and aggregating it, or you have a glacier that goes over and breaks it up into little pieces, and then it gets tumbled and eroded at the beach, and then you end up with something like this. So the first part of interpreting things that get embedded in here is considering where it came from. In our case, mostly seafloor. So when you look at the surface of this rock, which represents the seafloor at the time in the Middle Devonian, it's reasonably easy to identify these as some kind of shell. Well, they're obviously brachiopods, but if you didn't know that, you at least know some kind of a seashell. There's the butt end of a trilobite. Part of it's buried still, but I can see the axial lobe here and the side of the right side of the pygidium and so on. And we could probably find little crinoid stem fragments in there. Not so hard to identify fossils when you're seeing them like that. But if you turn the rock to, let's see here, its side, suddenly all of those shells and trilobites look like fossilized fingernails. They're just little bits and pieces in cross section. And if you're not thinking about them in 3 dimensions, you might think that that's some kind of hieroglyphics or some kind of, fossilized worm or something like that. And so most of what you're finding when you find a rock on the beach, if you see any fossils in it, there are 3-dimensional objects that are embedded. So it's not you're not going to find typically a fern leaf or a leaf imprint or any kind of hieroglyphics on a rock on the beach. Let's say take this fern fossil for example. This is an impression of a fern leaf. This was in a concretion that was split open. If this ended up on the beach, if this was a piece of rock that ended up in the lake and being tumbled by the waves on the beach, that wouldn't last more than a couple days. That 2-dimensional fossil, that imprint, would be worn away almost instantly. So the likelihood of you getting 2-dimensional fossils, things like compressed fishes or fern leaves or other types of leaves on a rock you find on the beach, the likelihood is pretty much zero or close to zero. So what may look like 2-dimensional fossils are 3-dimensional fossils embedded in rock that was once mud. So here's an example. I've made a makeshift brachiopod out of white clay, and it's sitting on the seafloor, and it's got mud up into the concavity there. It's sitting on the seafloor, and we'll just pretend this is a flat seafloor here. And over time, more sediment accumulates over it. Okay, you get more sediment accumulate over it. And then the glaciers break it off, and it's in the glaciers, and it's tumbling around. And then it gets in Lake Michigan, and it's tumbling around, and it's getting rounder and rounder, and it's looking less and less like the rock from which it came, and more like that you find on the beach. And at some point, it starts, maybe it cracks, maybe a piece cleaves off, or maybe it just starts to erode down to the fossil. So I'm going to use this knife to represent erosion past the fossil. And I've never done this before, so I have no idea. I have some idea of what it's going to look like. Now, I didn't cut deep enough. So there's where I've cut into the top of the shell, but if I would have cut deeper, it's going to look like a donut. And so now you've got a rock that may have had a fossil in it, and you look at that and you say, whoa, that's a fossilized calamari, from my appetizers at the restaurant. No, it's just a brachiopod that's been cleaved in a weird cross section that makes it look like a circle when it actually started out like this. It's just like taking a brain scan, like an MRI. You're taking it in slices, and if you slice it just right, you get something that looks like that. And of course, on the other side, you've got that, all part of the same fossil. A lot of times we find circular things that kind of look, straight like a coin or something. It's got these funny lines in it, and that ends up being a slice out of a horn coral. So if you slice that, you end up with a circle. If you slice it this way, you're going to get a totally different look. You're going to have longitudinal lines and little tabulae and little platforms in there and that kind of thing. And of course, if you slice it sort of not totally transverse and not longitudinally, but obliquely, you get sort of an oval. So this end here is more like a cross section, and this is more like an oblique section. And so you can get all kinds of weird shapes. If I were to take my model fossil here again and cut it this way, whoops, I get sort of weird shapes. I might get like what looks like a fingernail. Let's see if I can get another one here a little bit better. Yeah, you get your little chevron shape markings and stuff. So there's all different, when you get a rock and you're looking at it when it's been eroded and in cross section, you're going to get all kinds of weird shapes, and that depends on whatever fossil was there and in what plane you've cut it in. So these rocks that people call fossil soup or hash plates or detrital plates or death plates, when those get broken up and tumbled, you can see all the different kinds of interesting shapes, but those are sections of three-dimensional hard body fossils.
So I know somebody's going to ask, so what is this?
So
I think I know, but
I of course I subscribed to your video, so I saw the video I think when you found this one, and or at least showed it. This is where you had a fossil favicitid coral, so a tabulate coral, that was replaced. So this is the matrix, so this is the seafloor that it was in. The fossil occurred in this groove or depression here. It was replaced by iron pyrite, which tells me it was probably a deep, poorly oxygenated environment at the time. Most of the fossil has dissolved or eroded away, leaving this cavity, but you still have a few bits of the corallite that had filled with that iron pyrite and left this honeycomb-like pattern in its place. And you can see impressions of that pattern over in here.
all right, well, thanks a lot. So next time we see a fossil or a chopped off fossil, we might have a little better chance of identifying it. If you want to learn more about where the fossils come from, I'll link a video here, so click on that and I'll see you over there.